Hello, everyone. Bom dia a todas e todos. We resume our BRAG, Brazilian Algebraic Geometry seminar this year. And let me say that we decided that starting now, we are going to have the BRAG every other week, starting this semester. And it's a great pleasure to introduce our first speaker in 2022, Felipe Voloch, a Brazilian mathematician that is in New Zealand. And he will tell us about maps to the symmetric square of an algebraic curve. Thank you for being with us, Felipe, and the floor is yours.
Thank you very much, Carolina. Thank you very much, everyone, for coming. So I'm going to talk about maps to the symmetric square of an algebraic curve. This is a short abstract of what I'm going to be talking about. I'm going to be studying maps from a curve D to the symmetric square of another curve C squared, and the hope is to find a bound for the number of such maps under certain conditions. And I have to exclude certain things. I'll be precise later on. This is joint work with Jan Berg. The paper is on the archive if you want to look it up, but the main focus of the paper is slightly different from what I'm talking about today. It's a sort of more number theoretic question of local global principles for the existence of such maps, restrictions for the existence of such maps. But the result I'm going to talk about is in the paper, is a sort of a offshoot of the techniques that we used. All the details are there, but if you look at the paper, you may not recognize what I'm talking about at first. But if you go and search, you'll find everything's in there. But I wanted to, since this is an algebraic geometry seminar, I wanted to take out the algebraic geometry content of the result and talk about that. Here's the setup. So I have a perfect field of positive characteristic, and the reason is this reason here, why I'm working in positive characteristic. So I'm going to have two curves C and D over this field K. G is going to be the genus of C, and pretty soon the genus is going to be bigger. Well, at least we need the genus at least 2, because I want to talk about the Jacobian, and I want to embed the curve in the Jacobian, but I'm going to need genus at least 5, I think. It's going to be the bound that I'm going to need for the terms to have content. C squared with brackets is the symmetric square of C. So what is that? So you start with the usual Cartesian square, C squared, and you mod out by the action of the symmetric group that permutes the two coordinates. So that's the symmetric square. So you can think of it as parametrizing positive divisors of degree 2 on C. That's what the symmetric square parameterizes. And J is going to denote the Jacobian of C. And I want to study maps from D to C squared. And the reason I want to have the Jacobian is because I want to, so I'm going to embed C squared in J, right? So well, I need to choose a point on the curve. If I have a point on the curve, I can embed the curve in the Jacobian. I can also embed the symmetric square in the Jacobian using that point, and in the usual way. So I'm going to study maps D to C squared by studying this composition, right? Okay. One technical tool that I'm going to use a lot is the Gauss map. So I'm going to explain that before I even state my theorem. So if I have a map from, so D is a curve from D to the Jacobian. I want to construct another map from D to projective space dimension G minus 1. And remember, J is the Jacobian of C. So J has dimension G. And so I take a point in D. So this notation here is bad, but I'll take a point in D. So I have the tangent space to P at D, and I can take the derivative. So this is the same if the map is smooth and nice. This is going to be TFP of f of D. I guess I should write this, and this is what I should written here. So this is a line, right? D is a curve, so this tangent space is a one-dimensional space, which leaves in this G-dimensional space here, the tangent space at f of p to the Jacobian. Now, the Jacobian is a group, so you have the map J to J that sends P to, or it sends a point X to X minus f of P, right? So this is translation, and this map is going to translate f of P to 0, right? So well, what I'm trying to say is that the tangent bundle of the Jacobian is a trivial bundle. So the tangent space at f of p can be identified with the tangent space at 0 with J. So maybe I'll draw a picture. I have this Jacobian. I have a curve inside the Jacobian. I have a line. And then I have the line is a tangent line at f of p. But I want to translate the line to 0, so it becomes a line. So this is translate of TPD, if you like, and that lives in the tangent space of J at 0. So I can take projectivization of everything, and this line becomes a point in the projectivization of this vector space. So I get a map from D to PG minus 1. So this projectivization is a projective space of dimension G minus 1. So for every map from a curve to the Jacobian, I can associate this construction. Maybe I should call it phi sub f, right? So for every map f, I get this map phi sub f, which is from D to PG minus 1. And I want to use that. So if you start with if your D is C, right, and so J, remember, is the Jacobian of C. So if you think of C as embedded in its own Jacobian, you can make this construction. So you get a map from C to PG minus 1, and this construction recovers the canonical embedding. So you have a curve. Let's assume that the curve is not hyperelliptic, so we can talk about the canonical embedding. But if you do this construction of taking the tangent spaces to the curve inside the Jacobian and translating them all to the origin, what you get is the canonical embedding of the curve in PG minus 1. This is a classical fact. I don't even know who first noticed this. It certainly is in a paper of Andreotti where he gives a geometric proof of Torelli's theorem. So we can, this is a very classical fact that, the Gauss map in this context recovers the canonical embedding. So I'm going to use that later on. Okay, so this is the main technical tool that I'll be using. So now let me state my theorem, or my theorem of Jen. So I have to make an assumption that the curve has no linear systems of dimension 1 and degrees 2, 3, or 4. So that excludes hyperelliptics, trigonal, and curves of G1, 4. So it requires the genus to be large, right? So curves of small genus will have those linear systems. So if I'm assuming that there's no linear system like that, the genus has to be at least 5 or 6 or something. Okay, but the generic curve of large genus will satisfy this hypothesis. So this theorem applies to most curves once the genus is large. And I want to give a bound for the number of maps D to C2. So I'm going to prove that there's finitely many. I think there is a question here. Why is the symmetric square interesting? Well, it parameterizes divisors of degree 2. Maybe I'll come back to this question later. Or maybe somebody else can answer it in the chat. Okay, so I want to count the number of these maps. Well, maybe I'm not interested so much in the symmetric square. I am interested in the symmetric square, but I'm interested in maps from a curve to a surface. That's a well-known question. You want to impose conditions on the geometry of the surface to guarantee that there's only finitely many maps from from a fixed curve to that fixed surface. So for example, there's a question about whether surfaces of general type have only finitely many rational curves. This is a famous open question. And there's some results, you know, if the surface has sufficiently negative tangent bundle, then it's true and stuff like that. So, and this is a sort of a first case where we can actually prove something. So one of the first cases I know that you can get a result of an explicit bound for the number of maps from this curve to the surface. So let me state the theorem. So I want to look at maps which are separable. So remember, we're working characteristic P. So inseparability will cause problems. You know, if you have a map and you can compose it for Frobenius, you can get more maps. So you don't expect finiteness if you don't put the condition of separability. I have to exclude maps which are horizontal. So I'll wait a minute and I'll come back to this, what I mean by horizontal. But so I have to exclude certain maps. And the statement is that if I only look at separable maps that are not horizontal, then the number of such maps is this quantity, p to the r minus 1 over p minus 1. So I have an explicit bound, upper bound for the number of maps from D to C2. And what is this bound? Is this number here? P is the characteristic, so we know what it is. R is the dimension of this Z mod P vector space, which I'm going to explain a little bit what it is. Okay, so let me just unravel this definition, which is essential for understanding the theorem, right? So I guess the main point is that you have some finite dimensional vector space, and the R is the dimension of this vector space. So what is this vector space? So first of all, we have the morphisms from D to J. So all the maps from D to J. And I also have a subgroup. So this is a group because J is a group, right? J is an abelian group. So maps from D to J you can add at the target. So they are also a group. So now let me explain this part here. J to the 1 over P is the abelian variety you get by writing down the equations for J, taking the pth root of all the coefficients, and so you get a new set of equations. So it also defines an abelian variety, and is an abelian variety where the map taking coordinates and raising the coordinates to the pth powers land in J. So the Frobenius is the map that maps any algebraic variety to another algebraic variety by raising all the coordinates to the pth power. So J to the 1 over P is the source of the Frobenius map. And every time you have a map from D to J1 over P, you can compose, right? So if you have a map from D to J1 over P, you can compose it with Frobenius. You get a map from D to J. So, and this is what I mean by this. So the morphisms from D to the J1 over P can be viewed as a subgroup, can be mapped to a subgroup, or the morphisms from D to J. So this quotient here is just this group modulo this subgroup. And it turns out this is well, first of all, is a finite group and is a Z mod P module. And the reason for both these facts is the fact that the multiplication by P factors through Frobenius, right? So if anything that is inseparable factors through Frobenius. So multiplication by P is inseparable. So there's a map J1 over P, J. So this is the Verschiebung, this is the Frobenius, and this is multiplication by P. So if you take an element of this group here, the morphism from D to J, and multiply by P, you get something that lands in this subgroup. So the quotient of this by this quotient is, I guess, a quotient of morphism D to J modulo the multiples of P. And so it is a ZP vector space. And the fact that it's finitely generated follows from the algebraic geometries, it follows from the Néron-Severi theorem. For the number theorists, it follows from the Mordauvet theorem, essentially the same theorem, the finite generation of points of abelian variety on a global field. So this is long-winded description of this vector space here, and you take the dimension of it, and that's my R, and then you make this number here, which is a bound for the number of maps from D to C2 once you exclude the pathological ones. So what do I want to exclude? I want to exclude inseparable maps, so I want to look at only separable maps, and I want to also exclude horizontal maps. So what's a horizontal map? So remember, C2 is the C2 mod S2. So C2 has a picture like that. So that's the Cartesian square of C cross C. Looks like that. And of course, you have the actual horizontal things, which are images of things like that, and the vertical things. But since I'm taking the C squared modulo the permuting the x and y coordinates, horizontal and vertical are the same thing. So horizontal maps are also vertical maps, and I want to exclude those maps. So there are infinitely many maps from C to C2, like these things, right? So these things here at the bottom are maps from C to C2. If you fix a point P0, you can take any point P0, and this will give you all the horizontal maps. So actually strictly horizontal, maybe I should call them, right? So these are maps that are, comes from the Cartesian square and are strictly horizontal like this. But I also want to exclude maps that everywhere tangent to the horizontal maps. So in characteristic P, of course, you can have something that is not constant, but is always horizontal, right? So I want to exclude, I call a map horizontal if it's everywhere tangent to this actual horizontal curves. Okay, so this is the statement of the theorem. So let me go back to the statement of the theorem. I want to count maps from D to C to the symmetric squared C2, which are separable but not horizontal. And I claim that the number of such maps is bounded by this quantity P to the R minus 1 over P minus 1, where R is this number here. Okay, maybe I should give another perspective to what horizontal means and why we're interested in such maps, since there was a question about that. So let me just find a little space here. So suppose I have my D and I have my curve C. So to give a map from D to C2 is basically to give two maps from some curve to C. And in fact, what you have is diagrams like this, where this is of degree 2. So a map from D to C2 is also, it can be viewed as something like this. So if you have a curve D and a double cover of D prime, and a map from D prime to C. So if you have a map from D prime to C, and because this map on the left here is a double cover, it's Galois, so there is a involution that swaps the sheets of this map D prime to D. And so if you have a map G here, well, maybe not call it G, or call it H, and then you have the Galois group here is generated by the sigma. You have H and you have H O sigma. So if you have a map from D prime to C, you get another map from D prime to C, and the map induced by H, H O sigma is a map from D prime to C2, which descends to a map from D to C2. So another way to think about maps from D to C to the symmetric square is to think of all the possible double covers of D that map to C. And what I'm saying, and one way to think of these horizontal maps is to require that both H and H O sigma are separable, right? So a map is horizontal if one of them is inseparable, which I guess implies that both of them are inseparable. But so the non-horizontal maps are diagrams like this for which the map from D prime to C is separable. So these are non-horizontal. So these are the nice maps that I want to count, and I'm able to prove that there's only this many maps. Is there another question in the chat? Let me see. Eduardo is asking if I'm counting maps from D prime to C. No, because D prime is more. I'm counting, D prime is not fixed. Okay, in this diagram, I'm allowing D prime to vary as long as D prime is a double cover of D. So I'm counting all the double covers of D that have a map to C, a separable map to C. So it's stronger than counting the maps to D. If I wanted to count maps from one curve to another curve, I can use the Franke's theorem. And in fact, the techniques that I'm going to use to prove my result also give you the Franke's theorem with an explicit bound. So you can do that. But I'm doing more. I'm not fixing the D prime. I'm just fixing D and letting D prime vary over all the quadratic, all the double covers of D. Okay, so that's the theorem. So let's see how the proof works. So I have this map from, I want to start with a map from D to C2. So as I said before, the symmetric square parameterizes divisor of degree 2, so it naturally embeds in the Jacobian. So from this map, I get a map from D to the Jacobian. And so I get an element in this group. And I can take the one-dimensional subspace generated by this map. And I claim that I can recover the map from this information. So you see, I'm losing a lot of information. I'm starting with a map from D to the symmetric square. I'm embedding the symmetric square in the Jacobian. So I get a map from D to the Jacobian. And then I look, which is an element of this group here at the top. And then I look at the quotient group. So I have an element in this quotient group. I take the one-dimensional space generated by this element. So I'm losing information at every step, but I claim that I can recover F from this information, even less, because I have a map. So I have a map from D to J. So I have a map F. So I have a map phi F, which is the construction of the Gauss map. And it turns out that the Gauss map only depends on the class of F in this group. Because basically you're taking a derivative. So you're going to kill this part. The Gauss map is a derivative, right? Is a sort of the tangent directions of my map. So the Gauss map only depends on the class of the map in this quotient group. And this quotient group, as we discussed in the statement of the theorem, is finite. This is the finite thing that I'm looking at. And the one-dimensional subspaces is so this number here is the number of one-dimensional subspaces of a Z mod P vector space of dimension R. So that's what this number is coming from. And the claim is that I can recover my map F from phi F. Of course, I cannot recover my map F as a map from D to J. That would not make sense, right? When you go from morphisms from D to J to this quotient group, you're losing a lot. I mean, this set of morphisms is typically infinite. So this quotient group is finite, but the thing you're quotienting is not finite. But using the fact that the image of the map is on the symmetric square, I'll be able to recover the map. So I have the Gauss map and the fact that the image of the Gauss map is in the symmetric square. With those two bits of information, I'll recover my map. Something in the chat. Okay. Okay, so how am I going to do this? I'm going to use the Riemann-Kempf singularity theorem, which is a very classical. I guess what I need was proved by Riemann, but Kempf generalized it. Is that is a description of the tangent plane at a point P plus Q of the symmetric square. So the symmetric square, remember, lives in the Jacobian. So it's some surface that lives inside the Jacobian. It has a tangent plane. And you can translate this tangent plane to the origin. So it's the same construction as the Gauss map. You take the tangent plane of C squared and translate it to the origin. So you get a plane in the tangent space at the origin of the Jacobian. Then you projectivize it. So when you projectivize the tangent space at the origin of the Jacobian, you get this PG minus 1 that I'm using all the time. And what do you get when you projectivize this plane? You get a line, right? Which line? Well, there's only one line staring at you. It's the line that joins P and Q in the canonical embedding. So remember, the curve C lives in PG minus 1 is the canonical embedding. So there it is. And you have 2 points on the curve. So you have the line joining them. And this line is the tangent plane, or the image of the tangent plane of the symmetric square at the point P plus Q. Which means that as you vary P and Q, these lines sweep out the tangent, the secant variety of the curve. So the curve lives in PG minus 1. The secant variety is the union of all the lines joining 2 points on the curve. I guess it's a threefold generally. And this is called the secant variety. And this point phi of D, so remember, you have F from D to C squared, so you get a map phi from D to PG minus 1. And how do you construct this map? You take the tangent line to D at the point. So it's a tangent line to D, but D lives, the image of D lives in C squared. So this tangent line is contained in the tangent plane at C squared. So when you projectivize this point, the image, a point here, so D, a point X in D gets mapped to a point P plus Q in C2, and then that gets mapped to the line. Well, the point, well, it doesn't get, yeah, maps P plus Q, so, and it gets, there's a tangent line through this point, and so it's not in PQ, it's some point in there, right? So the tangent is passing through this point, and so the tangent line at D is in this tangent plane, so you get a point in the secant variety. Okay, so by using the fact that I have a map from D to C2, I get a map from D to the secant variety of the canonical embedding of C. Now here's an important observation, is that, so I have my secant variety, I have 2 points, P and Q, and the tangent to G at P plus Q is some point in this, is some point R in the line joining P plus Q. Now I claim I can recover P and Q just by knowing R. And that's an important step in the proof, that I can recover. So I have a point in a line. This line is secant to the curve. So there's this 2 endpoints. So the line is secant, so means that there's a line from P to Q, or P and Q are points on the curve, the curve C. And I claim I can recover P and Q from R. Why is that? Because if I had R another, so how would that fail if I had another pair P prime and Q prime here, and so another secant going to the same point R. If I had a picture like that, I wouldn't be able to recover P and Q from R, right? Because that would be P prime and Q prime would also give me R. But I can't have a picture like this. Why can't I have a picture like this? Because if I have two secant lines meeting at a point, these two secant lines are in a plane because they meet in a point. So there's two secant lines in the same plane. But that means that this divisor varies in a linear system of positive dimension. Because this isn't the canonical curve, you can interpret the geometric version of the Riemann-Roch says that if you have 4 points on a plane, it means that they vary on a linear system of positive dimension. So this is a G14. So a diagram like this, where you have two secants meeting at a point, gives you a G14. But I assumed, one of the hypotheses in my theorem was that I have no G14s on my curve. So this is excluded. So that's how I recover if I know the map D to PG minus 1, and it lands, or it actually lands in S, right? So S is the secant variety. D lands, the image of D lands in S. I can recover the map. So given this point R, I can recover P and Q, so I can lift it back to the map D to C2. So if I know this, what I call phi F, I can recover F. This only works if the R is not P or Q, right? So my argument here, I was thinking of R as a point in the middle of the line, not one of the two endpoints. And you have to be a little more careful if the R is on one of the endpoints. So that's why the theorem has this other hypothesis that I had to exclude horizontal curves, because if I have a horizontal curve, I mean, it could happen that the map is always, so you can, if the horizontal curve is mapping if you look at it, one of the endpoints is always, the R is an endpoint. So if you want to, a homework, see what happens in the horizontal curve case. See how the R becomes P or Q. But I'm not going to do that. It's if you look at the paper, the details are there, so you can see how it works. But that's the central idea: is that from this point here, I can recover from the secant. I recover the point in the secant. I recover the secant, and I recover the what's called the endpoints. So the 2 points on the curve that trace out the secant. So let me go back to this. So I start with a map from D to C2. I construct this map. By constructing this map, I only need information from this group here, which is finite. So if I have an element of this finite group, I have this map, and then I can use that to recover back my F. Any questions? I have a few remarks I won't like to make, but if there's any questions about the proof.
So may I ask a question?
Sure, go ahead.
So it seems that it could be more general, right? I mean, if I have a map to D to the P symmetric group or something like that, I mean, to the...
Yeah.
Yeah.
I expect so. I mean, it's a bit trickier to state, right?
Right. You'd look not at secant lines, but maybe secant planes or something.
Yeah.
And then assume something. Yeah, I don't know about the horizontality. Maybe there's something.
Yeah, we started with much more ambitious goals.
No, okay.
We actually wanted to look at arbitrary subvarieties of the Jacobian. And then we started sort of paring down. We had sort of geometric ideas, and we ran into a lot of obstacles to actually state a easy to state results. But yes, I'm totally with you. I think there's a more general version of this theorem. There should be even more general version that doesn't, we can take any subvariety of the Jacobian and use the Gauss map in the way that we do using to try and get something. But
right. And let me ask you, I mean, isn't it enough to assume that there is no G14? Or is there some subtleties with rational points, or I don't know?
So I need to assume that there is no, so for the theorem that I'm using, I need no,
Yeah,
so I need to assume that there is no G12 because I'm assuming that a curve is not hyperelliptic. I want to embed the curve in the Jacobian. I want the canonical embedding to be an embedding and not a 2-to-1 map.
But if
So
there's
I
no
don't,
G14, there's no G12.
yeah, okay. So I wanted to make it explicit: no G12, no G13, and no G14. Okay. Well, and the G1, and if you, so this step here that I'm omitting, which is when the point R is one of the endpoints, then I end up with situations like this, right? I have R, which is Q, and then I have a P, and maybe a P prime, and I want to recover this line, this R. And that's when I need no G13. So the condition no G13 appears naturally when you look at the argument, which is the same argument that I'm doing, but on the edge. But I wanted to, the reason I put no G12, no G13, and no G14 is that the condition appears, is a sort of similar, but appears in three steps in different ways. So there's one step where no G12, you can get past this obstacle, no G13, you can pass this up to G14. Okay. So I want to make a few comments and ask and pose a few questions, because I have in addition to the question that Eduardo already asked, where can we generalize it? There's a number of other questions. So first of all, a counterexample, right? So if you have a bielliptic curve, so what's a bielliptic curve? It's a curve that has a map of degree 2 to an elliptic curve. So if you have a map for degree 2 to an elliptic curve, you get a map from the elliptic curve to the symmetric squares, right? So you have a map you take a point on the elliptic curve, you lift it to a pair of points on C, and so it gives you a map from E to C2. So if you have a map of degree 2 from C to E, you get a map from E to the symmetric square. So a bielliptic curve, the symmetric square contains an elliptic curve. And an elliptic curve has lots of self maps. You can multiply elliptic curves as a group. So you can multiply by n, for example, for any n, and you get a map from E to E. So you can compose. So if you have one map from E to C2, you get infinitely many maps from E to C2. So that's a situation where the number of, and these maps will be, or not, they can be, if you assume that n is not prime, is prime to the characteristic, these maps are separable. These maps are going to be not horizontal, they're sort of diagonal, right? And so this is a situation where the finiteness theorem that I stated is not true. And the reason that is excluded is because this curve is G14, because the elliptic curve has maps of degree 2 to P1. So a bielliptic curve has G14. So this is excluded. Okay, another example is if you have a map, a curve defined over FP, you can take a curve defined over any finite field, but then you have to change it a little bit. But if you have a curve defined over FP, then the Frobenius maps from C to C, right? C to the power 1 over P is just C. So you have the Frobenius. So you have powers of the Frobenius. And you can take this map. Let me. C to C2, where you take the point P and F to the n of P for n equals equal to 1. And these maps are horizontal because when you take the derivative, this vanishes. So they're all sort of, they're horizontal. So this is an example of something that is horizontal, but not strictly horizontal. So it's not really at the horizontal line. It's just a map that is everywhere tangent to the horizontal lines. Okay, and these are infinitely many maps. So that's why I have to exclude the horizontal maps from the statement of ideal. Okay. And so these are the remarks I wanted to make. So it shows that the things that my assumptions are really necessary. Now, one assumption that I made right at the beginning was that I was working characteristic P, and that is necessary for my proof to work because it depends. So going back to the where the characteristic P enters is right here, is that this set is finite, right? So this when you mod out by the images of Frobenius, you get a finite set, and so when you take the derivative, you land in something finite. And of course, this is not going to be true in characteristic 0, right? So you can do a lot of the steps of this proof in characteristic 0, but you cannot use the finiteness. What you have is the morphisms from G to J, and what you're going to mod out by. You can mod out by the constant maps, right? So that would be the inseparable, the things with derivative 0, right? So the constant maps. But this is a finally generated group. But not finite in general. So in characteristic 0, you can still recover. So because most of my proof is geometric, right? So you can still recover a map from D to C2 from its image in this group. Right? There's the argument with the secants works just fine. But you don't recover the things that the things that this group is not finite. So you're not recovering the map from a finite amount of information. You have infinitely many choices. So the proof doesn't give you finiteness. But I would think that the theorem should be true in the well, part of the theorem, the finiteness statement of the theorem should be true. So that there should be only finitely many maps from D to C2 that are not horizontal. They're not constant, right? And not horizontal. I don't know how to prove this. So this is exactly the place, the point where I'm stuck. Right? One idea that I had, been sort of vaguely thinking about is you can try and prove it by reduction mod P. So if you have a situation characteristic 0, you can write it as over some finitely generated field, and then it makes sense to reduce it mod P. And you can arrange it by choosing the prime P sufficiently large that the set of because of this finite generation, you can organize things so that the reduction mod P map is injective. So you don't lose information by reducing mod P in terms of the number of maps. But what I don't know how to do is to avoid the situation where I start with a map in characteristic 0, I reduce it mod P and I get something horizontal. I don't know how to get around that. So I'm not able to prove finiteness because I could have infinitely many maps and they all reduced into horizontal maps. So that's one approach, is to try and reduce mod P. I have some ideas, but I'm stuck with this question of distinguishing, making sure that you not getting horizontal map. But also, if we can we get an explicit bound? Because the argument that I'm sort of sketching, or I'm suggesting that maybe it's feasible, would be to reduce mod p. You have to choose a prime p, and you have to exclude finitely many p's because there are some primes that will be bad reduction and so on that are not going to work. But I have no control over which prime I can reduce. So even if this thing works, I don't get a good bound because it depends on a prime p that is not naturally given to you. So question is, can you give an explicit bound? And yeah, so I'd like to see that. So I don't know how to answer these questions. There's the questions that I think are quite feasible. I wanted to mention briefly, I'm not going to write anything, but there are some questions in number theory about equations, even equations of the type ax plus by equals 1, but fix a and b, and you let x and y vary in a finally generated subgroup of the multiplicative group of a field. So you take, the multiplicative group of a field, and you take finitely many elements, take the finitely generated group generated by these elements, and you look at equations like this, where you take x and y in this finitely generated group gamma, whatever. And so this is very important in number theory. Lots of Diophantine equations reduced to equations like that. And there are bounds for the number of the solution of these equations that have been proved in characteristic 0, which are sort of c to the r, or c's of some fixed constant. So in one specific example, we have like 19 to the power r, where r is the rank of this group gamma. So gamma is finally generated group, so has a rank r, and you can bound the number of solutions of these equations by some exponential function r with a fixed base. And this has been proved in characteristic 0, Verzi and Schlickerwey, about 30, 40 years ago. But this was only characteristic 0. And then later, maybe 20 years ago, I proved a theorem in characteristic p, which was like this. But my bound was something like p to the r, where p is the characteristic. So it was worse than the bound in characteristic 0 was better because it was a constant to the power r. The constant is fixed, independent of everything. And the theorem that I could prove was something like p to the r, so very similar to this one. And then very recently, Pagano and Koymans, two students in Holland, proved in characteristic p a result that looks like the characteristic 0 result. So they removed the p and put the fixed constant. So they could bound solutions to these equations, the number of solutions, as 19 to the r. So the question of explicit bound here, you can ask in characteristic 0, is there a bound at all, right? So in characteristic 0 don't have finiteness, so you can ask, is there finiteness? And if we can prove finiteness, can we prove a bound? That depends only on the rank r. The r now is the rank of this group here. And in characteristic p, can we do the same thing? Can we get a bound that doesn't have the p in it? So can we get a Lepper bound for the number of maps that depends? Well, they have to depend on r, but maybe we remove the dependency of p. So I think that this is an interesting question that I at the moment I don't know how to do, but it would be good to do. And obviously the one observation I could make is that the bound is very far from being optimal, right? I don't have many examples of, I can write down curves with many maps to the symmetric square of another curve, but they are very, very far away from the upper bound that I proved. So, I don't expect this bound that I proved to be optimal in any sense, but this is a bound. And, but yeah, so here are some bunch of questions that I pose to you. Maybe some of you might be able to help me. And so maybe I should stop here. Muito obrigado.
Thank you, Felipe. So maybe in June, we will take you to the Shopee.
Okay, obrigado. Thank you.
So are there questions for Felipe?
I have more questions, but yes. So that's interesting. You said that the bound is not achieved, right?
Yeah, I don't think so.
Yeah, so you have a projective space, which is this, as I said, I mean, this PR minus 1 over P minus 1 is the number of points in the projective space. And if you look at the set of maps, it's some sort of something in that projective space. Maybe it's a variety or something like that. Could it have a smaller dimension or?
Maybe, I don't know. I mean, it's not. It's a vector space over Z mod P, so it doesn't have a. Right. You know, I don't know how to put the structure of a variety in it. So it really is Z mod P. You know, it's not. Exactly. You know, it's not a functor of. You know, you can spend scalars, but it doesn't mean anything, right?
Right. Yeah. So in principle, it's a finite set, but maybe there is some geometry as well.
Yeah. So I don't think, for example, if you have two maps to C2. Mm-hmm. Anyway, and you can look at them as maps to the Jacobian and add them, right? That's not going to be a map to C2. Right, so the subset of that I'm getting is much smaller. So what the first thing that I do in the proof is, okay, forget forget for the moment that the maps are from the target, the image is C2, and just look at the image being the Jacobian. By doing that, I'm starting to consider a much bigger set of maps. So first thing that maybe you can try and see is, what's the structure of this set, right? This set is not a subspace, right? So you can't add elements there. So already there you can, you'll be able to cut down the. Yeah.
I don't know. Let's see. Another question is, I mean, when you have an inseparable map, wouldn't it be horizontal?
Yeah.
Okay.
Yeah.
So you're already.
Yeah.
Okay. Yeah. Okay. Good.
But I wanted to make the distinction that you can have things that are horizontal that are separable, right? So.
Right.
Yeah.
Yes.
But yeah,
okay.
inseparable maps horizontal.
It's a stronger condition, not being horizontal.
Yeah.
Okay. Right. Okay. And you mentioned some horizontal maps, right? I mean, using the Frobenius as an example. Are these all the examples of infinitesimally horizontal, not horizontal, or something like that?
No, I mean, you can compose with automorphisms. You can sort of, and remember, you have a map from D to C, right? So you can sort of have, but essentially, that's everything is going to have to be built with something like that. So I expect. Yeah, that's essentially, you can make it more complicated, but not essentially more complicated, right?
Okay. All right. Nice. Thank you.
Thank you.
Are there more questions? I have a quick question. So you gave in this slide some examples to explain why your hypotheses are necessary. So are there also examples where you have infinitely many maps starting with a G13?
I would say yes, but I don't have. The answer to your question is no, because I don't have the examples. But I'm sure there are examples, right? So I don't know. But I would expect, I don't expect that you can, state a theorem that I think the geometry is going to be essential. Let me think. Yeah, because the G13, so we can try and use the G13 to get, so if you have the G13, so you have a one parameter family of triples of points. So you can map if you can map a curve from D to C, so you map into 1 point, and then you can take the complement, right? So if you have a parameterized thing of 3 points, right? So the G13 gives you, for every point on the curve, there's 2 more points, so that the sum of the 3 points is the G13. So if you have a map from D to C, right? So from every point of D, you get a point in C. You can take the 2 other points that in the triple, so you get a map from D to C too. So if you can make lots of maps from D to C, you can make lots of maps from D to C too. So I think maybe you can do something like that.
Okay, thank you. So are there more questions for Felipe?
There's something in the chat. We'll just, it's not a question. Thank you.
Ethan, thanking you. Yes.
Thank you.
So if there are no more questions, let's thank Felipe for this very nice talk. It's an honor to have you starting our brag this semester, Felipe. Thank you.
Thank you for having me.